Hi guys, Mr. Straub here. I'm not here. You can't see me at all. And there I am. Hi. Let's try that again. I've fixed all my technical difficulties and I'm ready to talk about ions and ionic bonds. So excited about bonds. Bond. James Bond. No, ionic bonds. Ionic bonds. That's what we're talking about today. We have a couple things we're going to cover. We're going to make sure that we understand what ions are to start off with. We are going to review the Lewis dot structures as we did on Friday. And then we're going to take a moment to talk about the octet rule, and in small case, the duet rule for helium. And then we're going to talk about how we can actually understand some chemistry using this stuff. All right, so the first thing we need to do is have a definition of the term ion. And an ion is an atom with an electrical charge. So let's take a look at an atom and see if we can make ourselves an ion. All right, so let's talk about a neutral atom of lithium. So we have lithium here. It is a neutral atom. It has 3 protons. It has 3 electrons. Those positive charged protons are canceling the negative charged electrons. And this is a neutral atom. That's why it says neutral up here. It turns out lithium is stable with 4 neutrons. It's also stable with 3 neutrons. Today, in talking about ions, we're talking about this charge up here. And it turns out most of chemistry has really nothing to do with the nucleus of the atom. There's some interesting things that happen there. Radioactivity, stars, and powering the entire universe. But on an actual day-to-day basis, most chemistry happens out in the electrons, out here in the outer shell of the electrons in particular. And so when you're learning about chemistry, what you'll find out quickly is it really has a lot to do with electrons and not a whole lot to do with the nucleus of the atom. And so the first discussion that we need to have about the chemistry of these electrons out here is what happens when you add and subtract them. Since that is so important, we've come up with a name for that, and we call that an ion. So let's go ahead and add an electron to our lithium here, and you'll see that we have turned this from a neutral atom to an ion. So an ion means is that it has a charge. And this is a negative ion because it now has 4 electrons, and it only has 3 protons. Seeing that it has 4 electrons, this is now more electrons than protons, and it has a negative charge to it. That makes it a negative ion. If I remove that electron, it's going to become a neutral atom. The 3 negative electrons are canceling the 3 positive protons, and it is neutral. What would happen if I remove another electron? Well, now it has become an ion again, but now it is a positive ion. Notice it is a positive ion because it has 3 protons. Protons are positive. It only has 2 electrons. When you compare those, you have an extra positive one, making this overall atom positive, and it's a positive 1. So what an ion is a charged atom that is either positive or negative. All right, so how do we make a positive ion? Ions that have lost an electron get a positive charge. Take a moment to think about that. It's kind of the opposite of as you should see, because you're subtracting, you're losing an electron, and it makes the charge positive. That's because there's more protons than electrons now. The negative ions are when you have gained an electron, and it becomes a negative charge. Take a moment, look at the model again, rationalize, think about why we call it that. We call it a negative ion because it has more negatives to it, more electrons. We call it a positive ion when it has more protons to it because protons are positive. Now, it turns out that most of chemistry has nothing everything to do with the nucleus and really even the electron shells themselves on the inner part of the atom. It turns out most chemistry has everything to do with the outer shell of electrons. And that is what we're seeing here in the Lewis dot diagrams. We ignore all the other shells that we saw in the Bohr diagram and we focus just on the electrons in the outer shell. We call those electrons the valence electrons, and those are the important ones, the really important ones when it comes to chemistry. And so if you look at group 1, these all have 1 electron on their outer shell. Group 2 have 2 electrons on their outer shell. This little divide right here is where the transition metals go. Their chemistry doesn't follow the patterns that we like to see, and so we kind of chunk those out as we introduce chemistry. Later on we can take some looks at some numbers and figure out what's going on in there. But for now we're going to ignore those ones. We're going to jump over to group 13 here. We'll see our pattern continuing again. 3 electrons in the outer shell. Group 14, 4. Group 15, 5. And then 6, 7, and then out to 8. Atoms become most stable when the shell, the outer shell, is complete. Now, it's a little different from helium because, as you guys saw when you're doing your Bohr models, that inner shell is completed too. That is why helium is a noble gas. Its shell is complete with the 2, and it is very stable. Neon's outer shell is complete with 8, and that is why it's a noble gas and very stable. Argon's outer shell is complete with 8, again why it's a noble gas. Krypton, same thing. And so all atoms are most stable when they can have 8 electrons around them. We call this the octet rule. Oct meaning 8, tet meaning thing it's trying to get to, thing. Just know it's trying to get to 8 to be stable. Now, neon, very stable. Argon, very stable. Chlorine and fluorine, completely unstable. What they really need to become stable is to get 1 more electron. They're going to get that electron from anywhere they can get it, and that's why these are so reactive. They'll try and steal that electron off of anything out there. On the other side of the periodic table, groups 1 and 2, these metals over here, it turns out that it'd be hard for them to get to the 8 of octet. And what they will do is actually lose this 1 electron to get down to the shell that's inside. So let's take a look at one of those and see if we can take a look here. Here is lithium. It's our stable, or it's our neutral atom of lithium, but it's very unstable as far as chemically. Its nucleus is stable. It's not going to radioactive decay, but it's very, very reactive. And what would make this more stable is if this outer shell was complete. Well, it's going to be really hard for it to get 7 electrons. And so what makes this more stable is if it actually can lose 1 electron. Now it's going to drop down to this inner shell. This inner shell is complete with the 2 electrons, and this is actually now a very unreactive element. And that's why lithium is most stable when it becomes a positive ion. And so it's very, very common to see it in an environment like this as a positive ion. It is very unlikely that you'll ever find pure lithium with an electron on this outer ring. It's highly reactive, and it's going to do anything it can to lose that electron and become a positive ion. In a similar way, this is fluorine here. Fluorine is a neutral atom. Again, highly, highly reactive because once it gets to that octet rule where its outer shell is complete, you can see it really just needs 1 electron to become stable. And once it takes that 1 electron, this has now become a very stable atom, and it's a negative ion. And so what you'll see is that things on the sides of the periodic table over here, these first 2 groups of metals, really, really want to lose 1 or 2 electrons. Become ions, they're going to become positive ions, and they are going to be stable then. On the other side of the periodic table, these 2 columns here, oxygen and its group, really, really want to gain 2 electrons and become negative ions. Fluorine and its group want to gain 1 electron and become a negative ion. And so what we see in nature out there is this side of the periodic table giving that one electron to the elements on the other side of the periodic table and forming lots of interesting chemistry that we call ionic compounds. All right, so what are ionic compounds by definition? The common name for these are salts. And salt that you guys know as table salt is sodium chloride. But there's magnesium chloride, there's lithium chloride, there's lots of different salts. In general, it's a bond between a metal and a non-metal. These all have very high melting points, thousands of degrees. If you take a salt and put it in your oven and try and put it all the way up to 500 degrees, you're not going to melt these. Even putting it into a flame often won't get these to melt. Very magical property they all have is they can dissolve in water. And we're going to take a moment to look at how that happens and what's going on there. And the interesting thing about ion compounds is the atoms of each other are attracted to each other due to the opposite charge of the ions. And so we can take a look at some salt in water and hopefully we can understand what's going on there. All right, so here we have some water and we're going to sprinkle some salt in here. And what we saw earlier is that we have sodium chloride here. The sodium here lost the one electron. It became a positive ion. The chlorine took it and became a negative ion. When they're in the crystal, they're stuck together because they are opposite charges. You have positive and negative charges hanging out next to each other. That's that ionic bond. When they go into water, something interesting happens. It turns out water also has a positive and a negative side to that molecule. So the sodium and chlorine don't need to hang out anymore. So as you put sodium chloride, see the crystal in there, as it hits the water, it will dissolve. It doesn't go away. The atoms are still there. They just don't need to hang out next to each other anymore. The positive sodium doesn't need to be next to the negative chlorine anymore because they can hang out with the water molecules that both have positive and negative sides to them. So when you sprinkle any ionic bond into water, a very interesting thing happens. They'll separate and then just float around. Now this only happens in things like water. If you took salt and put it into something else like oil, oil doesn't have a charge to it. And so you will not see this cool magical thing happen in oil. It only happens in fluids that are like water. Now, if I sprinkle enough in here, what I'm doing is I'm concentrating the amount of salt in the water, making this a more and more concentrated solution. And you're filling up that water with different ions of sodium and chlorine, and they're bouncing around, and that's fine. But eventually you'll get to the point where you've saturated the solution. As you can see, as you keep on putting more and more salt in there, eventually those ions won't have anywhere to go. There's just too many floating around in the water. And so what you'll end up forming is little bits of the crystal down at the bottom. Now, the crystal has a pattern to it. It has a positive next to a negative, next to a positive, next to a negative. The ions are attracted to each other. So if you put more ions in there, they'll dissolve, but as they bounce around, they will eventually bounce into that crystal that's at the bottom, and if they bounce in just the right spot, they'll complete the pattern and they'll stay there. If they don't hit in the right spot of the pattern, they'll just go away and more will come in. So again, watch, the salt goes in, it'll dissolve a little bit, and then it will pop in, and if it hits the other crystal, it'll continue the pattern. And this is why you can grow crystals. Crystals are patterns of atoms reoccurring, and they will continue to follow that same pattern over time. For class today, what I'd like you guys to do is this worksheet that I have. I'd like you guys to, in one color, draw the Lewis dot diagrams out for each of the elements you have here. Then, in a second color, I'd like you to circle the dot that is traveling across. Once you've done that, I'd like you to label the positive ion and the negative ion for each of these samples. So follow this pattern. Again, use two different colors. Show me your positive ion and your negative ion. Thanks, guys. Have a great day.